Well, greetings out there in YouTube land, and here we are with the third and final edition of our capacitor video series. In this particular episode, we're going to discuss the specific capacitor applications and amplifier circuits. We've already laid the groundwork for much of these explanations, and then I will go into a little additional detail on each where it is necessary. We'll also discuss the very mysterious way that electrolytic capacitors are able to not only have a high working voltage, but also a very high capacitance level. And since these two properties are antagonistic, we know this is quite a challenge, and there's a real tricky way that they accomplish it. If this sounds interesting, please stay tuned. And now, in response to countless viewer requests, we're going to have a nonpolar cat sniff-off between Jack, the cat, and Rusty, the wonder dog. Come on out, Rusty. See your fans. For our test, I've selected a group of old capacitors that I've removed from circuits. The two that I know are bad are these two waxy caps. Now, since the focus of this presentation is on capacitor applications to amplifier circuits, let's take a second here to discuss what those applications are. I've already alluded to several of these during my previous discussion, and we will get into more detail on the rest as we proceed. Number one, based on their ability to charge and discharge, just like batteries do, the battery in your car. They're useful to smooth out the ripple in our rectified high voltage DC, or B+, that we're going to use in our amplifier circuit. Now, although it's already been discussed in previous videos, let's have a brief review of how the filter capacitors smooth out the ripple from our rectified DC. We know that our rectifier tube or diodes are going to provide full wave rectification, but still with a significant amount of ripple in our high voltage DC output. The electrolytic filter capacitors will charge as the voltage rises and then discharge as the voltage decreases. This discharge will effectively fill in the gap between the peaks and smooth out the ripple. We also learned in a previous video that the electrolytic capacitors will fill in the ripple and charge the output to peak voltage, not to RMS voltage, which is why we sometimes find a much higher output from the high voltage windings of our power transformer than we might expect. Number two, based on their ability to block DC and pass AC, as we've already seen, when we apply DC to the capacitor, it will charge up, current will flow for a very brief period of time until the capacitor charges, and then no current can flow. Whereas AC, when it is applied to a capacitor, and we'll see this in just a second in greater detail, we'll see that the AC that is applied appears on the other side of the capacitor in almost equal measure. So it appears as if AC current can pass freely through the capacitor. Now, this is going to be essential for our coupling capacitors because we want to block the high voltage DC that's on the plate of one of the preamp tubes, say, and not pass it on to the grid of the next tube. Our signal is AC. We want to be able to pass the AC signal on from plate to grid, but we do not want to pass the high voltage DC plate current from plate to grid of the next amplification stage. Now let's see how coupling capacitors look in a schematic. In this case, a Fender Harvard. We see the coupling capacitors right here between the phase inverter and the output tubes. There's 0.1 microfarads at 400 volts. Now, why do we need them? Well, look over here at the plate of the phase inverter of the second triode of the 12AX7, we have 207 volts of DC. Now, if this coupling capacitor were not here to block that DC, it would come over here and just play havoc with the bias of our output tubes. You know how we have to very carefully provide bias voltage to these tubes so that they'll operate with a plate current that is within acceptable and optimum limits. Applying an extra 207 volts of DC to this grid, I think you'll see, would really screw up that process. So instead, we insert a coupling capacitor right here. It blocks the 207 volts of DC, but when our signal leaves the plate, it passes happily through the coupling capacitor and moves on to the grid so that it can receive final amplification before going to our speaker. Much has been said about Rusty's ability to sniff out bad capacitors. Well, let's see how Jack can do with this task. Let's toss out a bunch of vintage caps and let him perform a CAT scan on each and see if one of them catches his fancy. Yep, looks like that one, the white one. In fact, looks like he's going to pick it up and run away with it. Yep. And sure enough, it's a waxy old 0.01 microfarad cap that had failed many years ago. Looks like he is a successful cap sniffer after all. Looks like he's picked out another favorite here. And let's take a look at it. And sure enough, it's the other waxy early type of capacitor which had failed long ago. So looks like Jack's batting 1,000 here on old failed capacitors. As we just discussed, based on their frequency discrimination are capacitive reactants. They can act as high and low pass filters for tone controls and fixed tone modifications. In other words, you can hardwire in a particular size capacitor to eliminate any sort of harsh input signals. On record players, sometimes they will have filters to eliminate record scratch, things like that. This is based on the frequency discrimination capability of capacitors. And number 4 is probably the most complicated and challenging of the 4 different capabilities of capacitors. But hopefully at the end of the discussion, which is going to follow immediately, you'll say, hey, you know, that wasn't all that hard after all, I hope. Okay, let's keep our fingers crossed. But that is their ability of capacitors to shift the phase of the AC signal. All of that seems a little mysterious right now, but it won't be that mysterious in just a few minutes. Why do we care? Well, we use a phase shift oscillation loop for the tremolo effect in many of our amplifiers. I've already discussed tremolos in the different types in previous videos, but in this case, let's go into a little more detail on how the capacitors, and I think we've all seen the 3 capacitors in that oscillation loop. Why 3 and what do they do? Okay, let's look at that number 4 application, which is phase shift. Let's look at what happens when we hook up say a battery, a fixed DC power supply to a capacitor. We put a little ammeter here in series, and we can apply a voltmeter on either side of the capacitor. And then we're going to plot a graph to show the current and the voltage which we'll get from our 2 meters. I didn't draw a switch, but let's say we have a little switch here and we close it. Immediately, I think you can see the electrons are going to flow from our DC power supply through our ammeter to our capacitor plate. So the ammeter needle is going to deflect to show a flow of current, for a very short period of time, depending on how large this plate is. If the plate is huge, we might get a little current flow through here to last for a while. So our battery is charging up. The electrons are coming over here and accumulating on this plate, and our ammeter will show that. So let's look over here. Our ammeter is in red. It's going to rise up the current, and then once the plate is fully charged, the current is going to drop off and cease to flow. So I hope this is clear. Electrons will start to flow the minute we close the switch, charge the plate. Once the plate is full, once the bar has the maximum number of patrons, you start turning people away, the electrons can no longer fit on the plate, and it drops off to zero. This is the type of curve we'll see then on our ammeter. How about the voltage on our capacitor? Well, it's going to start off at zero, and shortly after the current starts to flow, and that shortly after is very important. We'll see in just a minute why. But shortly after the current starts to flow, the voltage difference will start to build up, okay? As more and more electrons arrive on this plate, the charge or potential across the capacitor is going to increase. It's going to rise up and reach a maximum, and it's going to stay there at whatever level the DC power supply charges it. Now this could last for minutes, hours, days, or weeks, but it will gradually decrease over time. I didn't have really room on this chart to show, but if our scale is correct, the charge would last out here for a very long time before it starts to drop off. I remember years ago I used this basic principle to get rid of somebody who was bugging me. They came over to my workshop and got in the way and started asking a bunch of silly questions, and I decided it was time to get rid of them. So I charged up a 350 volt capacitor using DC power supply and handed it to them and said, "Here, would you put this in the drawer over there for me?" And about halfway to the drawer, I hear a scream. I hear the capacitor hit the ground, and I hear the person leave, which of course was the desired end. So there's all different applications of this principle. Hopefully you will not be required to ever rely on that particular one. Now let's look at a very different type of graph and result when we apply AC to our capacitor. Now in this case, it's an AC power supply. It's going to rise and fall, positive and negative, in a rhythmic pattern here, in a sinusoidal waveform. Each time that this is the negative pole of our power supply, the electrons will flow through our ammeter, and just like with the DC power supply, the ammeter needle is going to tilt to the right as the electrons come over here and charge up this plate of the capacitor. And looking at our graph, we're going to see that here is our current flow as that plate charges up. Okay, then our polarity will change in our power supply. This will now become the negative pole for the power supply, and the electrons are going to flow down here and charge the other side of the plate. So if we are looking at the capacitor current flow, we see that it is going to rise up here, be positive. We're going to apply negative current, positive current, negative current, positive current. This waveform will be identical to the waveform of the input AC power. Now, since there's more than one waveform, we see this, 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 and this. It's tempting to think that current has passed through the capacitor. Let's face it, our ammeter needle is swinging back and forth, okay, and it's not a single curve that ends like it did with the DC, but it seems to continue. So it appears that the AC is passing through the capacitor, but at no time, because we have a dielectric here in between, At no time does any current really pass through the capacitor. It only seems to. Okay, we see then our current reading here that is taken from our ammeter. Now let's look at the voltage readings that we get across the capacitor. Okay, first off, notice that there is a little lag between the current being applied to the capacitor and the voltage arising across the capacitor plates. I think it stands to reason that as I start to send the electrons over here to the plate, there will be a slight delay between the deflection of the ammeter as the electrons flow and the increase of voltage as the electrons begin to accumulate here on this plate of the capacitor. Therefore, although the time lag is quite small, it still exists. So there is a lag here in the voltage increase across the plates. Then, as the polarity shifts, the voltage reading is going to shift. It's going to go from minus plus to plus minus. So here our voltage reading is going to drop down to the minus, come up here to the plus, come down to the minus, and every time it's hard for curves to be parallel, but in this case it's sort of like a parallel offset curve, which has that is the voltage related to the current, which has a lag, which is dependent on the amount of time it takes for this capacitor plate to charge. Now this amount of lag can be expressed in degrees. If we say that from this point here all the way to the peak of the waveform and down to where it returns to where it started, this is 1/2 of the AC waveform. This would be 180 degrees. And if we go all the way to the end of the waveform, where we have one complete waveform, then this distance would be 360 degrees. Now, this amount of lag, in this case, if from here to here is 180, I would say is probably what, 35 degrees of lag that I've drawn here. And if the voltage started out here in the middle, we could say that it was, what, 90 degrees of lag between the voltage and the current. This amount of lag here can be adjusted depending on the value of the capacitor and the resistor that we use in a high-pass filter. Now, in my tone stack video, I go into details of where you use a capacitor and then it's followed by a resistor to ground. That's a high-pass filter. So we can adjust this lag here from 35, 45, 50 degrees dependent on the value of capacitor and resistor that we use. This is going to be very important when we develop a phase shift oscillator loop to create tremolo in our amplifiers. And I will go into detail about how we do that shortly. Now, phase shift oscillator loops have been discussed in previous videos, but let's briefly review them again here so that we'll have completeness. We know that oscillator loops work by taking the injected signal and then using the plate output, we will feed it back into the grid so that we have the dog chasing the tail oscillation loop. The problem being, we know that phase inversion is going to occur between the grid and the plate. Therefore, if we feed in a signal that looks like this, the plate signal is going to be 180 degrees out of phase. So we will feed in a reversed phase signal, which in effect will cancel our input signal and will have no oscillation through our loop. So to solve this problem, Let's take our 180 degree out of phase signal and run it through a capacitor resistor network here of carefully chosen values to give exactly 60 degrees of phase shift. If you notice, the black line is the original input signal, the red line is the phase shifted signal. Now we'll run it through a second capacitor resistor network and we'll get another 60 degrees of phase shift. So now we have 60 plus 60 is 120 degrees of phase shift, and I think you can see what's going to happen when we run it through the third capacitor resistor network. We end up with 180 degrees total of phase shift, 60 plus 60 plus 60. Now the signal that is going to be fed back into our grid is exactly in the same phase as the input signal. It reinforces it, and now we can have oscillation within our loop. I hope it's clear up here that you can see the color differences. Here the black curve is the original signal as put out by the plate, and the red curve is the phase shifted signal shifted by our three capacitor resistor networks to give us the in-phase return signal to our grid. Okay, let's take a look at an actual phase shift oscillator in a schematic, in this case of a Fender Pro Reverb amp. We see that the signal leaves the plate of the first triode of a 12AX7, which is our oscillator tube, passes through a 0.02 microfarad cap and a 3 megohm potentiometer to ground. That gives us our first 60 degree phase shift. Then we'll go through the 0.01 microfarad capacitor and a 1 meg ohm resistor to ground, second 60 degree phase shift, and then another 0.01 microfarad capacitor and 1 meg resistor to ground, giving us a full 180 degrees of phase shift applied to a signal from the plate which was already 180 degrees out of phase. So we end up with an input signal to the grid that is 360 degrees out of phase, which we know is 0 degrees out of phase. And therefore the three capacitors in this loop have fed in a perfectly in-phase signal which allows our dog to chase its tail in a circle over and over and over again at a rate selected by the value of this potentiometer that suits our tremolo effect, slow or fast. Okay, Rusty's ability to sniff out bad electrolytic capacitors is well documented. Let's see how he does with nonpolar caps. These are the same ones that Jack sniffed. He has no interest. Seeing they're not dog cookies, Rusty's bored and completely uninterested. I think we have to award the grand prize for ability to sniff nonpolar failed capacitors to Jack. Okay, finally let's look at how electrolytic capacitors achieve what seems like an impossible task, and that is to have very high capacitance and very high working voltage levels. As we saw from previous discussion, this is just about impossible to do because the further apart you move the plates to get your high working voltage, the lower the capacitance. Or if you move the plates really close to get high capacitance, you lose a lot of your working voltage. So somebody came up with a really great idea how to have the best of both worlds. And as a result, we now have electrolytic capacitors to use in our amplifiers. So let's look at how electrolytic capacitors are constructed. First off, it's almost like a roll of toilet paper in which we have 2 ply of aluminum strips or layers here, plates, separated by a electrolyte soaked paper. It's all rolled up sort of like a toilet paper roll. And this particular plate is going to be called the anode, and this is why electrolytic capacitors have polarity. You have to connect the plus lead to the positive side of the circuit. Okay, so this is a dedicated anode. They can't take turns being the anode. This is one of the shortcomings of electrolytic capacitors, is they are polar and therefore have to be installed correctly. So on this side we'll have an etched aluminum foil plate. Why is it etched? Because if you have a smooth side or if you have a jagged side, the jagged side has more surface area. So they etch it to increase the surface area of the anode plate. And then on the other side we'll have an etched aluminum cathode plate. This would be the negative lead from the capacitor, or in can capacitors it's usually this is attached to the outer aluminum can, which you ground. There is an oxide layer on the cathode foil, and there is an aluminum oxide layer on the anode foil. The aluminum oxide layer is actually the dielectric, but rather than put these two plates together with that as the dielectric, in which case we would have very high capacitance due to the size of the plates. Remember, this is a very large roll of aluminum plate, but because the plates were so close together, if we put this plate over here right up against the dielectric, the working voltage, or the voltage rating of this capacitor, would be extremely low. So we space this plate away from this plate and the dielectric by interposing a rather wide, thick layer of paper which is soaked with an electrolyte. Now, an electrolyte is a liquid in which the positive and negative ions within that liquid can move about freely. They can go over and associate with this side here. The positive ions within the electrolyte are going to come over here and align themselves with the negative cathode, and the negative ions are going to come over to this side and align themselves by the positive anode. Now, what we've accomplished by inserting this thick layer is we now have a nice wide spacing between the plates to give us a high voltage rating for the capacitor. But you think to yourself, well, okay, but by moving those plates apart, haven't we really reduced the capacitance? Well, not really, because the electrolyte here, because of its ability for the ions to disassociate and go to either side, sort of acts like a conductor across this barrier and makes it seem like the two plates are really much closer together, right adjacent here along the aluminum oxide dielectric. Whereas in effect, where the voltage might try to jump across, it is spaced out quite a ways so that the voltage rating is maintained while the capacitance is also maintained at a high level. Now, down here I've drawn a diagram showing the ions in the electrolyte. Here the anions, the negative ions, have aligned themselves along the dielectric of the anode foil, the positive foil. The positive ions have aligned themselves here along the negative cathode foil. Now, look what's happened. The distance is bridged by the fact that the positive here creates a large accumulation of negative here, which then results in a positive ion concentration over here. What this plate thinks is that these positives are the anode plate, but they're not. The anode thinks that this line of negatives is the cathode plate, but it's not. So each plate then will have high capacitance, and the voltage rating will not be reduced because the electrolyte soaked paper actually bridges this gap and allows the capacitor to work as if the two foils were adjacent, when in reality they're spaced far apart, therefore preserving the high voltage rating of the capacitor. This is also why electrolytic capacitors have a finite lifespan, because even though they're very tightly sealed, when you have a liquid in here and soaked in paper, you know as well as I do that some of that liquid is going to be lost over time, and there will be some evaporation, and then the electrolyte will be lost, and the capacitor will no longer function as it should, because it will no longer have the electrolyte to transcend this wide space between the plates. That's the second shortcoming of electrolytic capacitors, the fact they have a finite lifespan. And the third thing is, you've heard about people using a variac to try to reactivate or reform electrolytic capacitors. What they're doing is applying a very low voltage across the capacitor and allowing the ions time to migrate to the proper either anode or cathode sides. Because the electrolyte's somewhat dried up, because the capacitor is no longer functioning as it did when it was brand new, it takes time for this to occur. So if you spend some time with a variac gently bringing this up to where the ions can migrate to create this type of relationship, the capacitor will probably still function pretty well as normal. If, however, you apply full working voltage to the capacitor, you could end up either with some sort of an arc or some other internal damage to the capacitor, and it could be permanently ruined. Therefore, the slow variac warm-up does have its advantages if your electrolytic capacitors are salvageable at all. Well, that's about it for this third and final edition of the capacitor video series. I hope that you found it interesting and informative, and that you will stay tuned for future video releases. Rusty, Jack, and I really appreciate the time that you spend watching and commenting, and we hope to see you again soon. Bye for now.